of straight lines and vectors. The first part of the problem is trivial. It is just about decoding the vectors, and that has been the recent fashion of J advanced in particular and mains in general. So let's see what does problem means. So consider line segments as follows. So first you need to appreciate why they are talking about line segments L1, L2, L3 and L4. So these are the equations. L is written, the equation of line segment is given in the vectorial form. So let's first decode this. L1 is such that R vector is 3ti. Now what is the meaning of 3ti? T is running from 0 to 1. So you can play with the question like this. Let's say if I keep t as 0, I'll get a point 0 vector in xy plane, right? If I'll keep t as 1, we'll get 3i cap. So we'll have 3i vector over this. Similarly, for t equals half, we'll have 3 by 2. Okay, so basically the tip of these vectors 3ti denotes a line segment starting from origin in the direction of I cap, and it spans over 0 to 3 length. Okay, so L1 is precisely the line segment which is drawn over here. So any point P which is between 0 to 3 comma 0 will be taken care of that by the first equation. Let's come to the second. This is 3i plus 5 rj. This line which is passing through 3 comma 0 here in the direction of j vectors, in the direction of I cap. So it's vertical line clearly, and there is a vertical span which is basically spanning through 0 to 5. So these vectors will start from 3i is a fixed vectors, and for r equal to 0 I'll get this point, for r equals 1 I'll get 3i plus 5, so exactly we'll get point over there. For r equals half we'll get this point. Okay, so it is basically locus of all points on this vertical line. I have to stop here because it's line segment, because r intersect 0 to 1. Similarly, L3 denotes again a line segment in the direction of j, as s is running from 0 to 1. So 0 will give you 0, and 1 will give 5j. So basically this segment is L3. What about L4? It's again a line which is passing through 0 comma 5 in the direction of I cap. And it's very easy to appreciate all this because you can decode R as x comma I, x I cap plus y j cap, and then it is 3t comma 0, right? So x will be 3t and y equal to 0. And since x 3t, x is running from 0 to 1, t is running from 0 to 1, that amounts to x running from 0 to 3. So that's another way of decoding this problems as a line segment. That was the first crucial part. L4 similarly is passing through 0 comma 5, so this guy in the direction of I cap. So in the direction of x-axis, parallel to x-axis, u is running from 0 to 1. So for u0, we'll get exactly this point. For u1, it's 5j plus 3i. So 5j is this side plus 3i, so you'll reach here. For let's say u half is 5j plus some 3 by 2i. So all these will know the point. Having recognized this boundary formed by L1, L2, L3, L4 is this region, right? So once we are done with this, let's move ahead. T be the rectangular region by these segments. Fine, we understood this rectangular. L1, L2 intersects at P. Now the only way where line L1 and L2 line segment will intersect, because for any value of T and R, they will never intersect except for the point of intersection at 3 comma 0. So I'm calling this point as P. L2, L4, that intersection is Q. L3, L4 is R, and L1, L3 is S. So we have this 4 point of intersection. Now the actual problem starts from here. A ball is projected along the line R vector equals T times I plus J. Again, I plus J is the direction which will be making 45 degree with this positive x-axis. So along this direction, a ball is projected on the horizontal table. Of course, this rectangle, because it's xy plane, so you can treat this as a horizontal table where there is a ball which is thrown at that angle. t greater than 0. T greater than 0 is to make sure like the direction of ball is in this direction, it's not opposite direction, because there is no table in fact there. So ball will be trapped in this carom board. Okay. Now next, ball collides with PQ, QR and so on. So of course the first collision that ball will witness will be with this wall PQ, it means with that line segment L2. Again, after reflection, ball will collide with RQ following the law of reflection, angle of incidence, angle of reflection. Then again it will come and collide with RS, and this collision will keep on happening, right? So it will keep on happening like this until ball comes and probably go to Q, and that's exactly is the question. So ball collides with PQ and so on. Let L be the total path length of ball when it reaches point Q for the first time, and let N be the number of collision. Then we have to find the ordered pair N and Q. You see, the major part of the problem was to understand the problem first and decoding these lines, which was not very tough, because once you have these vector equations, it's quite easy to decode this. Now the second portion is more crucial. So as you can see this diagram, which I've drawn over here, it takes a lot of time to do all those reflections here, because angle of incident, angle of reflection has to be the same. So is there a smart way of finding the number of collisions as well as the total length path? The answer is big yes. And that's very crucial, because one of the very basic ideas behind law of reflection is, let's say we have a ball which is projected towards this surface S, in this case is line. So according to the law of reflection, reflected ray will exactly follow the law of reflection. So if the angle of incidence is theta, angle of reflection will also be this. So they are going to be equal. Now one crucial point is, let's say the initial configuration or position of ball be P, the point of contact is Q, and the reflected ray is R. Now surprisingly, if we'll take the reflection of let's say reflected ray, which is R dash. So if I reflect this point R dash, PQ R dash must be collinear. And that can be proved very easily, because if this angle is theta, this angle is going to be 90 minus theta. Since I have reflected R over this mirror, so hence it's 90 minus theta, and hence this entire angle is linear pair, right? Because that angle goes to pi, it's 2 theta plus pi minus 2 theta, which amounts to 180 degree. Now since it's 180 degree, hence I can tell point P, Q and R dash will be collinear. Okay, so I'm going to use this repeatedly in this problem. Or vice versa, what we can tell, if I reflect point P, so again P dash, Q and R will also be collinear with the same result. So here we go. Now the crucial point is, and an ideal trick in these kind of questions will be, I'm calling it ideal because it's really perfect way of problem solving. For instance, here we have PQ distance was 3 and QR was 5, right? So instead of reflecting this ball in a box, what I do, I start creating copy of boxes. Now how we are going to analyze this? Let's see properly. So the first motion is from point P, ball was projected at an angle of 45 degree. Here I have changed the point notation, so I made it PQRS. Okay, just for the sake of simplicity of drawing diagrams. So when I first time the ball is projected and it is QR, after reflection it will exactly follow this part according to law of reflection. What I'm going to do with the previous idea is I'll reflect this reflected ray. Okay, and let's create another box over here. So I'm creating similar box 1 2 3 4 5 and 1 2 3. So you can see it's a square box of 15 cross 15 dimensions. 15 unit cross 15. The motivation is quite clear, because this reflected path can be mimicked as is this part over here, right? Again, I can assume if the wall would not have been there, the ball would have traveled this, and this length is precisely same as the length which it will travel after reflection. Now coming to this point, again, if the wall would not have been there, it will continue to move in a straight line, but here is reflection. So by the law of reflection, these two distances will be equal. Again, at this point, if the wall would not have been there, it would have reflected like this. So I can tell clearly this distance is same as this distance over here. And all points is going collinear because of the reflection. Again, at that point, if the wall would not have been there, simply it would trace this part, and by image principle, these two paths must be equal. So you see how smartly I'm able to see the multiple reflection here in a single diagram. Again, if wall would not have been there, the ball would have taken this path as shown in the diagram, and that's exactly equivalent to this. Similarly, at this junction, if wall would not have been there, ball will directly go and will try to hit this point, right? And that's precisely the point in the corner which I was talking about, is the point Q, right? So here we go, exactly what we are doing. So the first reflection is over here. Okay, so the first reflection when it goes from there is equivalent to this distance. So let me use different colors to highlight this. Second reflection is precisely here, this point. Third reflection goes there. Fourth is over here. Fifth bounce is there. And from there it's the sixth bounce. And that will directly go to the point, is the seventh. So I hope it's quite clear. And from here I can see the number of reflections that you need so that finally the ball reaches the extreme corner, which is mimicked over here, because this corner is same as this in its similarity transformation, the way I am transforming the situations. So what I can tell is how many boxes you have to cross. So basically you have to cross one box, the second reflection, second box, and third box, fourth box, fifth box, and sixth is the final eight, right? So first reflection comes here, let me name it. Second reflection is here, third, fourth, fifth, and in the sixth reflection, goal is done, right? So here the answer for n will be 6. And the path length is just this straight line path length, because that's basically equivalent to this zigzag path we have drawn over here, right? And this path length is simple to evaluate because this guy is 15, it's 3 into 5, and 5 into 3 is 15 as well. So total path length that we'll get is 15 root 2. Hence the answer for this beautiful problem is 16, 15 root 2. And this kind of technique is very important in problem solving, where instead of doing law of reflection, what you do is, instead of reflecting the rays, you make ray travel in a straight path, imagining there is no obstruction, and reflect the mirror itself or reflect the wall on which the ball bounces. I've given similar problems in my book, and wait for that. Till that time, if you have not subscribed my channel, please do it, because you'll get this kind of quality content here for free. Thank you. Have a good day.